All right, so reminders. Yesterday, we only covered one lovely unit because it was kind of a meaty one here, okay? So we started unit 3, and it's titled Working with Trigonomic Functions, okay? So again, reminding you that yesterday we dealt with the inverse trig functions, and again, it was kind of a meatier unit there, all right? Again, if you get stuck on something, if you have questions, let me know, especially, like I said, with the calculator stuff. I know that can get confusing, so please don't hesitate to reach out if you've got questions for me, all right? But today, let's get into it. All right, we're going to go through 3.2 and 3.3, or as far as we can get in that time. All right, but these are going to be the units you're responsible for finishing tonight. 3.2, which is solving trig equations, and then 3.3, which is talking about this thing called a harmonic motion, which I'll introduce to you. All right, and then that finishes up unit 3 here. So again, I would suggest you do lesson 3.2, 3.3, and then if you're feeling comfortable and confident, you can go ahead and take your test, or you can save your test for the next day. But regardless, remember, tomorrow we're going to move on to unit 4 here. All right, so that's kind of our pattern, is about 2 lessons a day, and then we finish a unit in 2 days here, okay? So again, just reminding you of some of these things here that you can help pace yourself, all right? But again, now that we understand a lot of what's going on with these inverse trig functions, okay, we can now use them to solve equations, all right? We can use them to solve equations, and this one's called to pi or not to pi, all right? And hopefully you'll understand what that means, again, because we're talking about unit circles, and unit circles are, again, if we go around an entire unit circle, it has a radius of 2 pi, okay? So again, reminder, hopefully by now we understand these basic trig functions. And again, our calculator is going to be our best friend for a lot of things. However, when it's asking for exact answers, or if you're restricted to not using your calculator in the future, you've got to be able to do some of these tricks offhand, right? Or, you know, with a basic calculator, you could figure them out here. Okay. Someone used to tell me that your calculator is only as good as the person operating it, right? So again, you've got to make sure that you know what you're doing before you plug it in a calculator, right? The calculator is just a tool. All right, so we're going to look here kind of quickly in this unit, because I know you've done a lot with sine and cosine and tangent, but we'll still go over how to solve these trigonomic functions here. All right, so if we're looking at 2 cosine of x minus 1 equals 0, hopefully you're starting to generate some ideas of what the heck you have to do in order to solve it. All right. So you would need to first obviously isolate the cosine of x by itself by adding 1 to both sides and then dividing by that 1/2. So it's going to give us our cosine of x equal to 1/2. All right. Then basically we're going to find every place where the cosine function is equal to 1/2. All right. We've done a couple methods. We talked about looking at our graph and finding those intersection points. We talked about looking at a unit circle and those coterminal angles, right? And then we talked about just picking, you know, maybe the first 2 here, okay? But regardless, and whenever we do this, we have our 2 solutions to the original equation here, all right? Assuming that we're staying in our 1 circle, right? So again, the 2 pi or not to pi, right? So if we're staying in our 1 unit circle, right, within our units of 2 pi, right, 2 pi, then these would be our only 2 answers that satisfy this cosine of x equals 1/2. Okay, so then again, if we try to use this in your graphing calculator, and I introduced this to you yesterday, okay, if you try to put this in your graphing calculator, all right, it will give you your answer here, all right, it would give you your answer of 1/2. Same thing if you did for the 5 pi over 3, it would still give you this 1/2 value, right? But we talked about yesterday, I'll back it up to this one. Okay, we talked about yesterday here how if I plugged in inverse cosine or cosine to the -1, right? If I plugged in cosine to the -1 on my graphing calculator, it would give me out a decimal, and it would only give me the value for this pi over 3, right? It would only give me one decimal, and it would give me this value for pi over 3. Because when your calculator does things, it tends to stay in quadrant 1. All right, so it would be up to you to figure out, well, what the heck is point whatever, or whatever, what is this fraction? What does that stand for in terms of exact values using pi? And then obviously, what would its second solution be, right? Where we have those, using this reference angle of pi over 3. All right. So again, perfect. The solution the calculator doesn't give you can be found using the unit circle. Okay, so again, the calculator would only give you that pi over 3, and it would not give you 5 pi over 3. So you'd have to use the unit circle and understand the reference angles. Okay. So then, of course, yesterday we talked in general, if we're going beyond 2 pi, right, in either direction, we can write our equation starting with our first angle and then plus or minus this 2 pi n or 2n pi, right? Because it's talking, of course, about the repeating nature, all right? So this is, again, if we're moving outside of 2 pi, right? 1 unit circle. And again, n represents all integers, so just whole numbers. +1, -1, all of that stuff, all right? So then there's another type of problem where we might have to collect like terms. So obviously, if we look here, we've got a cosine of x. All right, on both sides. So first off, we would combine the trigonomic functions to put cosine on the same side, and I'm left with 2 cosine of x. All right, and then obviously we can solve the rest of the problem from here. We move our square root of 2 to the other side, and then we divide by 2 to obviously isolate that cosine of x. All right. But then once we've done that, it's the exact same problem, right? You figure out what values work, either using a graph, using your calculator, using a unit circle, right? Any of these different methods here, all right? And you find your 1 or 2 original angles given to you using your unit circle, right? Given to you using your unit circle, all right? And again, when you're using your calculator, it would only give you one answer. It would only give you one answer, all right? And you would have to either, again, use your reference angles, use your knowledge, a lot of different reasons. Again, why this is potentially why your graphing calculator isn't always the go-to answer for a lot of this stuff here, okay? So again, using this correctly. All right, and then like we said at the beginning, all right, we'd have our 2 original points and then plus or minus that 2 pi n. All right, again, we worked a lot with that yesterday as to why that works. All right. Moving forward here, if we had to use a square root function, okay, again, we're still trying to isolate our x variable here. Okay, so we get the 1 to the other side, we get 3 to the other side, and then what we can do here is we can take the square root of both sides here. All right, and something I want to point out is that this is actually tan of x squared. All right, this is actually tan of x squared, so don't let it confuse you here. All right, when you take the square root of tan squared x, it's just tan of x. It's not tan of square root of x. All right, so again, this is like saying tan of x times tan of x. All right, but you can still take the square root of it, and then we're left with an equation that we know what to do with. Right now, again, we're going to look for our original equation. Our equation here. We can plug it into our graphing calculator. We can use our unit circle. We can do a lot of different things, but we're going to look for the points at which tan gives us this square root of 3 value. All right, and something that I want to point out here though is that because we had to take the square root, right? Because we had to take the square root, we get the positive and negative version of our answer. All right, so again, because we had to take the square root, we got our positive and negative answers. So that would be why there are 4 answers to this one instead of 2 like we're more comfortable or used to. All right, but regardless, all right, understanding that we're now looking for 4 solutions, it's the same process. We either look for the intersection points or we understand our unit circle and understand what angles those could be found at. All right, but once we find our solution here, okay, once we find our solution, All right. Again, this is the other way of looking at it. You can look at your unit circle, understand that it's here and there, and then understand the reference points. Okay, understand that the reference points will give us the same values on both of those angles. Okay. But again, once we've gotten our 4 angles, either using, you know, our unit circle method or using our intersection method, we then write our answers. If we want to extend beyond just that 2 pi unit circle, we write it every original value plus or minus 2 pi n, right? Plus or minus 2 pi n. All right. Then we can do factoring, right? We can talk about factoring, and hopefully we remember from all of the work we did with quadratics here, this zero product property, right? And again, to remind us, that's what happens when you have 2 things multiplied together and they equal 0. So either A can equal 0, B can equal 0, or there's a chance that they both equal 0. Right, so again, this is how we solve for a lot of problems with our quadratics, right? But if we look at this here, okay, obviously, all right, obviously we want to collect like terms. Okay, we're going to collect like terms. So we'll move tan to the other side. All right, then we can factor out a tan term, right? So we factor out our tan term. And then we can use our zero product property. Again, remembering that if we treat things like if tan of x is treated like one property and sine of x minus 2 is treated like another. Okay, so we can get these 2 separate equations where we can still solve for x being in tan or in sine. All right, so moving forward here. All right, I wish they would have done this a little bit better here. All right, but I guess they're starting with tan of x equals 0. Okay, so if we went back to the equations, right? So tan of x is equal to 0. Before I started moving to this, I would have solved for this sine squared x minus 2. All right, but regardless, they're looking at tan here first. All right, but know that obviously we have to finish this sine squared x minus 2 equals 0 equation. All right, but regardless here, once we've gotten to the trigonomic functions of tan, right, we're looking for where tan is equal to 0, and obviously it only crosses 0 at 1 point, right, and it's at intervals of pi. Right, we know that it's crossing at intervals of pi, right? So we've got 0, pi, 2 pi, all of that fun stuff. So again, we could start with our original plus or minus n pi, right? Plus or minus n pi, and since our original is 0, okay, we just write it as plus or minus n pi, plus or minus n pi. Right, and obviously for this one, it's not 2n pi, right, because it's at every pi interval, not at every 2 pi. All right. So then there also has to be the answers for where we have sine squared x minus 2 equals 0. So, okay, we have to solve for sine of x, and again, they messed up here. Okay, so this should be sine of x is equal to plus or minus square root of 2, right? Because what they did is they moved 2 to the other side in this first step, then they took the square root of both sides, right? And again, when you take the square root of sine of x, okay, or sine squared x, that's like saying, again, sine of x times sine of x. So we get rid of one of them, right? And we should be left with sine of x is equal to plus or minus the square root of 2 here. Okay, and when we plot this one, right, or if we were able to look at our unit circle, we would notice that there's no values, okay, either positive or negative, that will satisfy this equation. So what that means is there's no solutions for sine squared of x where this will be true here, right? So there's no equations where that will be true. All right, so what you could do there is you could just write no solutions, right? You could write no solutions. All right, and if we were to combine this here, obviously, we would, when we combined this, we would look at our solutions of tan and our solutions for sine, and since there's none from sine, it would just be the answers from tangent there. All right. And then if we're dealing with cosine of x, okay, if we're dealing with cosine of x, right, we can look at it in this quadratic form here, okay? And when we look at cosecant, right, we can notice that they are looking like quadratic equations. Okay, they're looking like quadratic equations here. All right, so what we can do is we can treat them similar to quadratics. All right, so when we look at these quadratic equations, okay, we can examine them and think of it, like I said, like a quadratic. All right, and the form that they're saying here is 2a squared minus a minus 1, right? If we just treat cosine of x like a variable. All right, and when we're able to do that, we're able to factor out our expression here is 2a plus 1 multiplied by a minus 1. Or replacing our a with cosine of x, we just treat it as these two different equations here. All right, and then again, same as we did on the last slide, we're able to use our zero product property rule, set both of those equal to 0, solve so that we get cosine of x is equal to different values here. All right, and we can look where cosine of x is equal to -1/2 and where cosine of x is equal to 1. All right. And again, using the same methods that we've talked about through the last couple of slides here, we find our angles on our unit circle, right? We find our answers on our unit circle, and then we would be able to write it using that 2 pi or plus or minus 2 pi n form, right? So again, showing you the other way of doing it graphically or using the unit circle here, okay? And that would be for our first cosine of x is equal to 1/2. All right, and then we would solve for the second half of this equation, and that would be where cosine of x is equal to 1, right? And so it's equal to 1 at 2 points here, all right? It's equal to 2 points, and so when you generalize it, it's going to be at every 2 pi point. All right, so again, when we write them, we can add them with this infinitely many beyond our 2 pi restrictions here. Okay, then hopefully we remember those identities that we got introduced to, right? So we had an identity here of sine squared x plus cosine squared x equals 1. All right, so that was an identity that we found that was true here. So what we can do is we can use them and substitute in for our trig functions. All right, so I know that sine squared x plus cosine squared x equals 1. All right, I can move it to the other side here. Right, I can move it to the other side here. So what I can do then is in my original expression here, oh, they went a little quickly. Sorry. In my original expression here, instead of having cosine squared x, I can plug in 1 minus sine squared x. Right, I can plug in 1 minus sine squared x. And then what they did was they distributed out the 2, and then they got this new expression here in terms of all being in sine. Right, in all being in sine. And what this is going to do here is this is going to allow us to collect like terms, right? So that was the whole point of this in the first place, was changing either cosine or sine so that we could collect like terms and not have to deal with two totally different trigonomic functions, especially when they're being added together, right? When they're being added together. If they were multiplied, right, we could use our zero product rule and not be a big deal. But when they're added or subtracted, right, we have to substitute in to replace for 1. So once we replace this in, we can then combine our sine values, right? We can now combine our sine values, or we can make it look like our quadratic, right? So if these had the same values, right, it was just sine, we could maybe look, we could combine it and make it look like a sine function. All right, but unfortunately this is sine squared x and this is sine x, right? So we can't just immediately combine them, so we have to treat it like a quadratic. All right, but once we've treated it like a quadratic, zero product rule, we know how to do that. All right, and again, I'll let you go through these slides here to remind yourself. I just want to keep us moving for the sake of time here. All right, So then if we're looking at a different one, we can do more substitutions. So for example, if I have sine of x minus 1 and cosine of x, all right, we have both sine and cosine in this equation. So what we can do is, again, we can try to use this identity of sine squared x plus cosine squared x equals 1. Right, we can try to use this identity. So what we can do is we can square both sides of our original expression, right? And that's totally fine in terms of mathematical operations, because again, as long as you do it to both sides and you're equal with what operation you're doing, it's fine to do. So what we do is we square both sides. So now we're with sine of x minus 1, that quantity squared, and we've got cosine squared x, all right? And then once we do that, we can now use our trigonomic function of sine squared x plus cosine squared x equals 1, right? So again, we simply rearrange this expression here, all right, to solve again for cosine squared x. Once we've got it in a form that we can substitute, we've got cosine squared x and cosine squared x, all we do is we replace the value, all right? Once we've replaced the values, we can collect like terms, right? Distribute what out we need to, we can collect like terms, all right? And then we have our quadratic expression, right? We have our quadratic expression here, all right? And we can then factor out just like we do with a normal quadratic. We've got 2 sine x times by sine x minus 1, okay? We can use our zero product rule. All right, we can use our zero product rule and have both of those factors equal to 0. And then obviously we know we would solve for sine of x. So 0 divided by 2 gives us 0. This one here, we're going to move that one to the other side. So we're looking at where sine of x is equal to 0 and where sine of x is equal to 1. All right. And again, once we get it in these forms, we know how to do the rest of the steps here, either using our graph or using our unit circle. Okay. Now here, we might have something with a multiplied coefficient, right? So if we look at tan of 9x equals 3, tan of 9x equals 3, right? This right here has a coefficient of 9x here. So we'd have to isolate that, obviously, outside of this trigonomic function. So what they're saying is you have to extract this term from it, right? So we're trying to, of course, solve for this. Okay, so this is where we're going to have to use our inverse relationships here to solve. So if I have 2 sine of 5x minus 1 equals 0, okay, I am going to, right, we notice, okay, notice 5x is inside that sine function. So we're going to have a way of undoing our sine function here, all right? But what we can do is we can replace 5x with a single variable in order to make it a little bit easier for us at the beginning. We just have to remember to replace it back when we're done. But we start off here, we have our 2 sine of a minus 1 equals 0. All right, what we're going to do then is obviously isolate sine here. Okay, isolate sine by itself. We're left with sine of a is equal to 1/2. All right. And what we can do there is now find those values, right? We can find those values, all right? Again, using our inverse knowledge here. Okay, and we get those values of pi over 6 and 5 pi over 6, all right? We can get those values there. However, remember that a that a, of course, stands for those values plus or minus the 2 pi n, but we have a equal to 5x, right? We have a equal to 5x. All right, so we have to take that into account. So once we figured out what a is equal, we have to replace a with 5x in our solution and then solve, right? So if we replace our a here with our 5x, we can then solve for our values here, right? We just solve for x. So we divide both sides by 5, and so this is what we're left with, pi over 30 plus or minus 2 pi over 5n, right? We do the same thing with the other expression here, all right? So once we found our values of a, the trick was plugging back in our value of 5x for a and then resolving. Right, so again, hopefully not too terribly different, just a little bit of finagling there. All right, and then if we look at this expression here, okay, we've got 5 tan of x over 2 plus 5. Again, it's going to be the similar thing here, except we replace our x over 2 with a variable. They chose w for this one, right? It was a for the last guy. All right, but once we replace it, okay, we treat it just like we have been, and then we can solve for our tangent function. All right, we're going to solve for our tangent function where it's equal to -1. All right, once we solve that, okay, it's in forms that we're used to, right? So those are our two solutions for it being in terms of W, right? Again, you can look at your unit circle and look at that guy. All right, but remembering that W is equal to x over 2. W is equal to x over 2, right? So what we'd have to do is we would have to replace W with our x over 2 term again, right? So we replace it, and all we do then is solve for x. And in this one, we multiply each factor by 2. All right, and we do that for both of the solutions that we found, and then we are able to get our expression here. Okay, so again, really trying to keep track of what you're replacing, what it's standing for here. Okay, and looking back at the real world here, right, as always, okay, you can look at the depths of an ocean, right? And we're going to deal a lot more with real world examples here. But again, the trick here is can you solve these in your equation, or sorry, can you solve these using your calculators, right? Can you follow the order of operations, right? And again, I personally like to write it all out by hand before I plug it in my calculator, because then you can isolate things and move them around a lot easier. Okay, looking at our study guide here. All right, looking at our study guide. Again, a lot of this is based on the specifics, okay? So a lot of this, as you can see, is based on the specifics from each of the work, all right? But in general, once you've isolated it, right? Once you've isolated it using whatever methods, right? Normal algebraic skills, right? Moving things to the other side and just isolation, or replacing it using a trigonomic function, or replacing the variable with another variable, right? Whatever your process is once you get down through that, okay, once you get through those processes, it's the same exact steps every single time, okay? It's the same exact steps every single time. Of course, we have a checkup here, but again, for the sake of time, it's going to be a lot of practice problems. All right, and like I said earlier, I know that some of these can get really, really daunting. So what I would suggest is, all right, at least with some that look the same, like sine and sine here, maybe just pick one. Right, you can just pick one, or cosecant and cosecant, you can pick one here. All right, but really you need to make sure that you're not just dealing with the first problem, because obviously you should know this, right? Problems get more difficult as you go down in the sections. Okay, so obviously this one here about cosecant looks a lot more complicated than this original just sine one. Okay, so again, give these a good try here. And they're all going to be based on the same process. Okay, isolate the variable as best you can, right? Then try to solve using your unit circle or using your intersection method. And then if you need to go back and replace those values because you had a swap at the beginning, then you're going to go and do that. All right, again, make sure that you try some of these, especially these units. This unit here it's a little bit more involved as we go on. Okay, so again, always making sure that you're trying these to check yourself. All right, so we do have this one quiz here for solving trigonomic equations. Okay, so you are responsible for doing this one quiz. All right, moving forward here, we're going to deal with this simple harmonic motion. Okay, so simple harmonic motion, and I don't expect you to know what a harmonic motion is at this point. If you do, awesome. All right, but it is a periodic motion, right? It is a periodic motion. So we can talk about it through a lot of different ways, and I don't know why the audio is not working on this one. Okay, but there's a lot of different waves that we can talk about harmonic motion. All right, so waves in an ocean, right? That spring and the jack in the box. Okay, I can't remember what these are called. want to say something pendulum, right? But basically, you're going to find out it's a periodic motion, right? It's a periodic motion that has to deal with this wave-like behavior, all right? And it might not seem obvious at first what or how a spring here might have a wave-like nature, because it's just going up and down here, all right? But we can define simple harmonic motion, all right, as, again, the periodic motion. And they're going to use some bigger words here, but basically what's going to happen is if you move in one direction, all right, you're going to move back to your original starting point here. All right, so if we look at the oscillation, okay, you go down and you come back up to where you started. Okay, you go down and come back up to where you started. All right, and again, you will deal with this in physics class this coming year, right? You'll actually get to model this looking at different masses. How does it change the stretching or compression of this? All right, but something I want to point out here is that obviously this one's going on and on and on forever. All right, if you've ever dealt with springs or slinkies or whatever, you know that eventually they stop, right? And that's because of gravity, that's because of friction, right? That's because of air resistance, a lot of different things here. But when we're talking about these for math class, we're going to assume that they're perfect systems where they don't have any of those factors for most of the point, most of the things we're going to talk about here. Okay. So if we look at this mass on our spring here, okay, again, we said it starts at a point, and you're going to notice it's always going from 4 to -1, 4 to -1, 4 to -1. As long as nothing is working against it, right, it should be perfect forever and ever and ever, all right? But again, as we talked about, in the real world, there are things like friction and air resistance. All right, but again, assuming our system is perfect, if we put a pencil to this and actually try to model what it looks like graphically, as our spring goes up and down, hopefully you're noticing it's making a wave-like behavior, right? And it doesn't perfectly, or it may not perfectly at this moment look like a sine or cosine function, but it's having a repeating pattern that's going on and on and on. All right. And obviously, if we actually did this and got a better simulation, okay, you would be able to see that it actually is a cosine or sine function, right? Because we talked about a lot how cosine and sine are very similar with just a slight movement of where they start. All right. But the two equations that we can use here are a cosine of WT or a cosine of a sine of WT, all right? Again, A and W are just constants here, all right? And again, you'll talk more about this in physics, but as you know from your experience in chemistry class, some of these variables, right, are Greek letters, right? So this could be the Greek letter for a different function here. So don't let it confuse you if it's curly or not curly, right? It's just a variable, all right? But if we look at the two equations here, taking a second, all right, we've got a cosine of WT or a sine of WT, all right? Regardless, the amplitude, right, the max displacement is going to be the value of A, and that should be familiar to us, right? Amplitude, the displacement from the equilibrium or from that middle point, right? So from the middle to the top or the middle to the bottom, that is our amplitude, and that's going to be that value out front, our A value, our constant value. All right. Since we're dealing with sine and cosine, our periods are 2 pi. Right? Our periods normally are 2 pi. All right. But as we found out when we were displacing our sine and cosine functions in that earlier unit, I think it was unit 2, right? We're going to divide by W if there's a factor in there for our period. So it's going to be 2 pi over W. And then our frequency, all right, if you don't remember from chemistry class, our frequency is the number of oscillations per time, right? Or how many times it goes up and down per 1 second. So a cycle per second. All right, and our frequency for this guy is 1 over our period. And again, that should be kind of familiar, hopefully. 1 over period here. So all we do is we take it and we flip this equation. So we've got W over 2 pi. all right? Because this is our oscillation per unit time, right? And when we're dealing with our unit circle, okay, we're always dealing in terms of 2 pi, right? We're always dealing in terms of 2 pi, okay? So if we look at this example here, okay, I've got our coiled spring 4 inches from the equilibrium, and if the oscillation is 3 seconds, write an equation that describes its motion. All right, so we'll look at what that looks like here. Our equilibrium
Consider
position,
a spring with a
the equilibrium position is in black there.
mass attached in equilibrium position. Draw a TD plane so that the t-axis corresponds to time and the d-axis corresponds to displacement. This will align the t-axis with the equilibrium position as seen here.
Okay, and again, you'll investigate more about this spring later in physics. All right, but awesome. So when we pull our spring all the way down to our lowest point, it'll bounce up to the 4 here. All right, and again, as you can see, the equilibrium will always be the middle point because that's halfway between -4 and +4, right? So our amplitude here, if you look at it, our amplitude is 4, right? Our amplitude is 4.
Suppose that an object attached to a coiled spring is pulled down a distance of 4 inches from its rest position and then released. Assuming simple harmonic motion, how will the displacement function look?
Okay, so again, we know that we have our displacement function here is dealing with an amplitude of 4, all right, but it's not starting at 0. So since it's not starting at 0, it is not our sine function. It is not a sine function, all right, because sine usually starts at 0 and cosine starts at 1, all right? So since we're starting at a non-zero number, we know we're dealing with cosine, right? And since we're starting at -4, it's going to be our negative cosine, right? Our -4 of cosine. All right. Given that the oscillation takes 3 seconds, this means that the period of the function should be 3 what? All right. What is 3 equal to? And if we go, let me go back. All right. Our period is equal to 2 pi over W. All right, our period is equal to, and I'll write these down for us here so we can see it. All right, our period is equal to 2 pi over W. All right, and our frequency is equal to W over 2 pi, or 1 over our period. All right, so I'll put those here so that we can see them. All right, so apologies.
Suppose that an object attached to a coiled spring is...
All right, so we found out again, cosine, awesome. All right, again, the oscillation takes 3 seconds, so the period of this function should be what? Right, so it should be 2 pi over W, right? And our W there is 3. All right, so it should be 2 pi over 3. All right, 2 pi over 3. All right. And what is our frequency equal to? Our frequency is equal to the inverse of that. All right, so our frequency is 1 over our period. So it should be 1 over 3, right? 1 over 3. All right, again, the reason it's 3 is because it took 3 seconds to get back to where we were, right? Took us 3 seconds to get back to where we were. So our period was 3 seconds, right? So W had to be that 2 pi over 3 in order to get rid of those values. Okay, so then determining which equation to use here, right? What if we have different variations? All right, so if we look at our positive, right, starting at 0 and going in the positive, or if we look at negative here, right, we have potentially 2 variations. All right, we have potentially 2 variations. All right, But as you found out, okay, as you found out, sometimes there's infinitely many answers, right? So if we started with the positive or the negative, it would just depend on which one they gave you. If you got to design your own, right, that would be something that you get to decide. Even though it has the same nature, right, you could decide if you wanted to start in the positive or the negative direction here. Okay, we'll fast forward through this one. Okay, so then here's a couple practice problems here. So I will let you guys do this practice on your own. I wish they gave you more practice in the pre-calc, but I think this is a really good one for you guys to try here. All right, but again, do not let these giant words confuse you. Okay, displacement, that's just how far it's moving, right? Is the object sinusoidal? That's talking about, is it sine or cosine? All right, so again, sometimes I personally get lost in some of these bigger words, so read it, figure out what it's asking you, and then try to solve it here. Okay, so doing those practice problems are going to be super helpful for you. All right, now if we move forward here, we look at the motion of a pendulum. Okay, a pendulum, you're going to find out it is the same thing. All right, it is the same thing. It's just changing the nature of which it looks like. So, apologies. All right, so a pendulum is something that'll swing back and forth. And right now it's got this length of L. Okay, so as you can see here, the amplitude, okay, the height is given by this angle of theta. All right, and it's based on obviously our length L here. Okay, so our arc length, as we found out, right, is determined as a factor of our length times by our angle, right? Our length times by our angle, because again, we're dealing with a rounded length and not a perfectly straight line here. All right. Obviously, for small angles, the arc length and the horizontal displacement are very, very close. All right, but as we get larger, it's going to play a drastic role here. Okay. Okay, when we're dealing with small lengths here, we can just assume that it's about the same, which is really, really nice for us. Okay, so we can assume that this is the same for smaller lengths. If we were to pull this guy up to say here, obviously it would not be the same there, right? So we would have to deal with that accordingly. But for small ones, for small angles here, we can deal with it being like a straight line here. So that's a way of thinking about it. All right, so if we have this displacement, all right, if we have this displacement and we look at our oscillation, okay, we look at our oscillation. All right, the motion of our pendulum looks very, very similar. Okay, it looks very, very similar here. All right, and again, they changed the way that the drawing was made. So I know it looks like it's going up and down right now, but imagine this is going left and right. I imagine it's going left and right like the pendulum. Okay, so pendulum there will have the same equations. Okay, we'll have the same equations because it's making the same motion, right? It's making the same motion. All right, the only difference here is that we could have L and G now be involved, right? So when we're dealing with things in the real world, right, especially when we're dealing with things going in an up and down motion or the swinging motion, right, we have to take into account gravity, right? So again, same equation here, all right, but what we can do is we replace our W value here, replace our W value in terms of our length and our gravitational force, right? So we just update our frequency and our period equations just slightly here, all right? So again, we can look at these different properties. All right, property one, the pendulum of equal lengths, the initial displacement does not affect the period, all right? So it's going to be the same period if it has the same length. All right, so notice that the red and the black one, even though one goes higher than the other, they still cross at the same point. Okay, so it's more determined based on the length than it is how far you pull it. All right. Then property 2 here. All right. Like I said, period depends on the length of the pendulum and the gravity. Okay, so that's the second one. If you've got one much shorter than the other, it's going to have a greater period than the one that's longer. All right, so then you can look at this example here and walk yourself through it, but it's showing you, all right, I'm going, I've got a 20 centimeter pendulum, right? So its length is 20 centimeters. All right, the weight at the end of the pendulum is released from a position of 36. Right, it goes 36, swings to the 14, right, and it swings back. Okay, so you would have to then solve for the rest of these equations. All right, so again, thinking about what's the equilibrium, that's what is the middle point, right? It's asking you what is the middle point? What is the angular displacement, right? So what angle are we going up by, right? What's our period? And then of course, what is our horizontal displacement? Assuming it's that straight line for us. Okay. And then of course, this practice problem, I really want you to try on your own here. And then talking about, of course, like I said, in the real world here, okay, it's not always perfect. All right, it's not always perfect. So we can pretty much always assume that there is this thing called friction or air resistant. All right, but as I told you, when we're dealing with it mathematically, most of the time it's easier to assume that there is no friction or air resistant. All right, However, as it says here, okay, that's quite restrictive, okay, because it doesn't take into account a major factor. It doesn't take into account a major factor, right? So when people are actually designing, right, they go from real world and then they have to account for such things like air resistance and friction, all right? So you can deal with like a piston in your car, right? So you actually have to take those into account. But what's really cool is that sometimes if you take into account, you can actually make those forces work for you, right? So you can make the force of gravity work for you. You can make that resistance work for you. Like something that I'm thinking about is what are they called? Oh shoot, I can't think of what the exact word or phrase is, but basically the wheel that spins in the water picks up the water, right? And basically what that does there is that makes hydropower, right? It makes water-based power. And we can actually harness that energy of the natural movement of water and then gravity. We can actually harness that and use that for energy here. Right, that's a cool way of utilizing processes that are, again, in nature. We just take advantage of them for the benefit of humanity. All right. But again, with this study guide here, okay, this is going to be really helpful for you, especially with those equations here. All right, especially with those equations. Right, so I think that was mostly page like 6 and 8 here. All right, but answering all these questions are going to be super helpful, making sure that you understand how this process works here. All right, because you have obviously this checkup and this quiz here. So if we look at the checkup, okay, it's going to be talking a lot about pendulums, right? It's going to be talking a lot about pendulums. It's going to be talking about springs and everything that it has this oscillating motion, right? Again, the repeating motion up and down like a wave, and it's going to have either this sine or cosine function here, all right? It's going to have either this sine or cosine function, all right? And again, we have this relationship that we can understand, and we can figure out our amplitude, period, and frequency. All right, we can figure all of those out. And the last little tidbit I have for you is if you're given an equation like this, if you're just absolutely stuck on what to do, you can treat this d variable like a y. You can treat this like a y here. So you can actually just plug this into your calculator. You can plug this into your calculator. All right. However, you can't have two variables here. You can't have two variables. So it would have to have at least a variable for your W. But if you can figure that out, then you can plot it and look at what that shape of the graph would look like. If you're, especially when you're being asked questions like what's the amplitude, period, frequency, right? Sometimes it helps to see it actually graphically, right? So again, if you get it in this form here, you can plug that into your graphing calculator. All right. Again, I really highly suggest you always check your answers, at least do a couple problems here before you get to this quiz. All right. So we just finished 3.2. We finished 3.3. So you've got those two quizzes, and either tonight or tomorrow, if you're feeling adventurous here, right, you need to wrap up Unit 3. Okay. It's got obviously the review of the content. It's got the calculator review, which again, I cannot hype this up enough. Yes, calculator skills are super important, but you still have to know what it means. All right. You should do a couple practice problems, but this is of course extra credit. So if you want to do this practice, it's extra credit. So is the discussion here. It is extra credit. The only thing that you have to do is the CST here, okay? The CST. So again, tonight, tomorrow, you need to get finished with 3.2, the quiz, 3.3, the quiz, 3.4, the CST, okay? And this should be unlocked for everybody, so you shouldn't have any issues here, okay? So that ends our class today. So again, let me know if you're having an issue, if you want clarification on something, if your test isn't unlocked, any of the above. All right. But other than that, guys, I will see you tomorrow. Again, please let me know if you have any issues, and I'll talk to you guys then. All right. Goodbye.